In the present lecture, we are going to explore the topic when the linear charge density varies on the ring, then how we can find the total charge of the ring, okay? So before proceeding with that topic of electrostatics, we must understand what is the meaning of azimuthal angle or the azimuth. See, whenever you have a ring, say we have a ring like this, and we are making any reference diameter, say something like this, okay? And this I am taking as the reference line, that is the reference diameter, and there is a point on the ring, on the circumference of the ring, say P. So the angular position of P, if you are making a line joining center with P, so this angle will denote the angular position of P with respect to this reference diameter, and this is called the azimuth or azimuthal angle, okay? So basically the azimuthal angle is the angular position of any point on the ring with respect to any reference diameter. Now according to the rule, if this line you are taking as the reference line for phi, so for this point the value of phi will be 0, and since you are denoting phi on this side, on the left side, so this side will be taken as the positive direction for phi, and this side will be taken as the negative direction of phi, okay? So when you will come at this point, say you are covering a quadrant of the circle, okay, you are covering a quadrant of the circle, and when you cover the quadrant and you comes to the point A, so for this point A the azimuth will be what? How much angle you covered? Pi by 2. When you cover a further quadrant, you will reach a point B, and for B you can judge the azimuth will be pi. You have covered an angle pi with respect to this line. And when you come at a point C, okay, C is center, say I am giving it a point D. So when you comes to the point D, your phi will be pi plus pi by 2, that is 3 pi by 2. And ultimately, when you are coming to the final point, that is coinciding with the initial point, your phi will be 2 pi. So this is the azimuthal angle for each point on the ring. You can see that for each point on the ring, the azimuthal angle is continuously changing, correct? For each point on the ring, the azimuthal angle is continuously changing, and the range of the azimuthal angle is 0 to 2 pi. For one revolution, your azimuth angle will change from the value of 0 to the value of 2 pi, correct? This is the range of the azimuthal angle. So azimuthal angle is basically the property of a point on the ring. It varies for each point of the ring. And if any quantity depends on the azimuthal angle, again I repeat, if any quantity depends on the azimuthal angle, it will change from one point to another point on the ring. It will change from one point to another point on the ring, and point to point variation means continuous variation that will call for the application of calculus, okay? So I guess it is clear what is the meaning of the azimuth or azimuthal angle on the ring. Now see the next point. Let's see the application of this azimuthal angle in electrostatics. Suppose we have a ring like this, and this is the reference line, one of the diameter which I am taking as vertical. So this is the reference line, say for measuring the angle phi, and I am taking an element. I am applying the concept of calculus. So I am taking an element on the ring, something like this, which we have learned in the basics of calculus. So this is the center, okay? Say this linear length is L, and if this is L, the linear width would be DL. Say this angular position is phi, that is the azimuth or the azimuthal angle, and this angular width is d phi, and the radius is r, okay? And this element, this green element, has a charge dq, correct? So this is how we denote the element, a calculus element, infinitesimal charge on the circumference of the ring. So this is what you can say charge element. Okay. Now we know the basic of mathematics. If this is theta and this is r and this is s, so s is equal to what? R theta. So in our case, if this is a circular arc with a length dl and this is r and this angular width is d phi, so we can always write dl is equal to what? R d phi, correct? Always remember, this is something very basic of calculus which will be applied frequently in mechanics, electrostatics, electromagnetism. So whenever taking the element on the ring, so dl can be written as r d phi. The charge on this element, so from the basics of the linear charge density, the charge on this element dq can be written as what? Lambda dl. So dq will be lambda dl, and you can also write dq as what? Lambda, and instead of dl we can write what? R d phi. So this is the value of the infinitesimal charge on this element. Okay. This is how we write element of the ring, lambda r d phi. D phi is what? The angular width. Lambda is what? The linear charge. Now see, now it depends what is the subsequent step. It depends which quantity we have to find. Now suppose you are finding the total charge. So if you are finding the total charge, so it would be simply the integral of dq, correct? Now if you are finding the electric field, okay, now suppose we want to find the electric field, then first of all this dq will be treated as a point charge, and we will find the infinitesimal electric field dE due to dq, and then the total electric field will be the integral of dE. This is of course the vector integral about its component along different axes. Third is, suppose if you want to find the electric potential, so same approach as we applied in the field, dq will be treated as a point charge, and we will find dV due to dq, and the total potential will be integral of dV. Got it? So all approaches are correlated, okay, and symmetrical. We'll see base problem how we can find the total charge on the ring when lambda is given as a function of the azimuth. So let's see the problem. Now let's see the problem. The linear charge density on the charge ring depends on the azimuth angle as lambda as a function of phi is lambda naught cos square phi, and lambda naught is a constant. You can write here lambda naught is constant. Find the electric charge contained in the ring. Now in this application we will have one integral. I don't know whether you know this integral or not, so just for the recap I'm revising it. Suppose we have to integrate cos square phi d phi, correct? So this is not in the standard list of integral. Had it been cos phi, then the integral would be sin phi, correct? But this is cos square phi. So we know the formula. Cos square phi can be written as 1 plus cos 2 phi by 2. Okay, and sin square phi can be written as 1 minus cos 2 phi by 2. Okay, these are the basic trigonometric formulae which I've already told many times in the classes. If you don't know, you can write here. Okay, number 1. Number 2, we have seen in integral, if you are doing the integral of like something like cos 2x dx, your answer will be sin 2x, and then you have to divide with the coefficient of x, that is 2. Okay, so if you are integrating cos 2 phi d phi, the answer will be sin of 2 phi by 2. Got it? This will be your answer. This is the second point which will be applied. Third point, we know whenever you write sin n pi, n belongs to any integral value 1, 2, 3, 0, minus 1, minus 2, minus 3. So sin n pi will always have a value of 0, correct? So these are some of the basic things will be applied. So see, suppose we have to integrate this quantity cos square phi d phi from phi 1 to phi 2. So I can convert it in the double angle. I can write 1 plus cos 2 phi by 2 d phi, correct? Within the limits phi 1 to phi 2. This integral will come to be, I can take half outside. So it will be d phi plus cos 2 phi d phi. Okay, phi 1, phi 2, phi 1, phi 2. Okay. Now what will be the integral of d phi? So the integral of d phi will be phi within the limits of phi 1 to phi 2 plus the integral of cos 2 phi. So cos 2 phi will have an integral sin 2 phi, and further we have to divide with the coefficient of phi, that is 2, within the limits phi 1 to phi 2, correct? So this integral will come to be half phi 2 minus phi 1, okay, plus I can write half sin 2 phi 2 minus sin 2 phi 1, got it? So this is the value of the integral of cos square phi d phi from phi 1 to phi 2. I did it separately so that you are clear about how we do this integral. Got it? Okay, now let's come back to the problem. So here lambda is with phi. So if I'm making the ring, okay, and I am taking any reference line. If no reference line is given, you can take any reference line, okay? If in the problem no reference line is given, so this I am taking the reference line for phi, that is on this line phi is equal to 0, okay? Now I am taking a charge element on the ring. So I am taking this element on the ring. This is the center. This length, linear length is L, linear width is dl. The angular position, that is the azimuth, is phi, and this is your d phi, and the charge on this element is dq. This is of course your calculus element, infinitesimal element. So we can write dq as what? Lambda dl, and dl we know the basic r d phi. R is the radius. So therefore dq will be what? Lambda r d phi. Let it be equation number 1. This is the charge on this element, correct? This is the charge on this element, that is small element, elemental charge. Now the problem demands charge. So the total charge will be integral of dq. So it will be integral of lambda r d phi, correct? Now the question is that whether, what you think, whether lambda will come out of the integral or not. So it depends, and in the present problem it won't come out of the integral, because in the present problem lambda is variable, it is continuously changing, it is given as a function of the angle. So in our problem lambda is given as lambda naught cos square phi, correct? So therefore the charge will be lambda naught cos square phi r d phi. Okay, now in these parameters you can judge easily what are the things, what are the parameters which can be taken out of the integral. So lambda naught is a constant, r is a constant, of course phi is not a constant, phi is the azimuth angle which is changing continuously on the ring, and it is integrated with respect to phi. So now we can put the limits of phi 1 to phi 2. Now what do you think, what will be the limits of the azimuth angle? Correct? So you will be starting from this point, and this point is phi is equal to 0, correct? And you will go for whole of the ring, completing the whole circumference and coming back to this point. So already I have told you, for the complete ring the azimuth angle runs from 0 to 2 pi. So the limit of azimuth will be 0 to 2 pi. So it will be from 0 to 2 pi, and this integral already I did, correct? I told you this is half phi 2 minus phi 1 plus half sine twice of phi 2 minus sine twice of phi 1, okay? So I can write this integral as half phi 2 minus phi 1 plus half sine of how much? 2 phi 2 minus sine of 2 phi 1. Correct? Now we have to put the limit. Integral I have done before, so already you have noted how to solve this integral, correct? So here I am putting that value. So my value of charge will come to be lambda naught r half, what is phi 2, 2 pi minus phi 1 0 plus half sine 2 into 2 pi, that makes 4 pi minus sine of 0, correct? And right now we have seen the sine of any integral multiple of pi is 0. So sine 4 pi, sine 3 pi will be 0, sine 0 will be 0. So this will have a value of 0, this will have a value of 0. So this term will exhaust it and it won't give any contribution. So your q will come to be, 2 will get cancelled away, pi lambda naught r. So this is your answer. This is your answer to this problem. Got it? Pi lambda naught r. So this is, we have seen how we can find the total charge on the ring or any arc of the ring. Suppose instead of the whole ring we are given any arc, so simply the value of phi will change. Phi will depend till what angle the arc is given. In this complete ring, phi, the azimuth would run from 0 to 2 pi. So if the lambda is given as a function of the azimuthal angle, what you will do, you will take one element, will find dq, lambda dl, and dl will be what? R d phi, and then you can integrate for finding the total charge. Got it?